In the last section, you review the environmental factors that influence fire behavior. We looked at some of the resources available to you when you're analyzing your fuel, weather, and terrain conditions. But even with those resources, predicting fire behavior is difficult. In today's environment, we hear more and more experienced firefighters saying that they are seeing fire behavior that's more intense than anything they've ever seen before. New terms are being thrown around such as area ignition, wildland flashovers, simultaneous ignition, and explosive fire behavior. If this is true, if conditions are really changing on the fire ground, how does that affect your ability to predict fire behavior? Let's listen to some professionals from both the wildland and structural world talk about fire behavior at the high end of intensity. Bob Kittredge specializes in teaching wildland firefighting to many structural firefighters.
One of the things I've been looking at is how, in my teaching, is how to get structure firefighters, because when we looked at some of the structure firefighters, the majority of their training is in structure. So what I looked at is how do I get them to understand what's happening in the wildland arena? One of the comparisons that I've seen is the flashover compared to what's happening in the wildland arena with whatever we call it, simultaneous ignition, area ignition. Something where the fuels in that given area are igniting at the same time. It's not a rate of spread, it's not fire progression, it's a simultaneously ignition. Is that an option? I don't know, but there's something there that's really keying me into something's happened that's catching people off guard.
This summer started out, or I should say the spring, ended up on the Ham Lake fire in Minnesota. And, Minnesota, early season fire, didn't expect much. Incredible fire behavior. I mean, spotting, this is observed spotting up to 6-7 miles, rates of spread that were just, running behave. I couldn't get the behave model to predict what was going to happen on the ground. It would reach its wind limits, it would top out, it wouldn't go any further. And then that recurred all summer long. And I kept talking to firefighters, guys saying like, that was by far the most, most incredible spotting I've ever seen. These talking about cascades of embers coming off one tree and immediately starting, 2,000 spot fires right there. And then it was this exponential growth, because then you'd have 4 or 5 trees torch off, thousands of spot fires, and just things happening so quickly. I think was the, fires are getting bigger, faster, and then these conditions for that area ignition, which I saw this summer, you could see a whole hillside that would suddenly become this carpet of fire. Rates of spread, for instance, on the Wine Cup complex, we had an afternoon, the conditions were light winds, moderate temperatures, relatively speaking, but we had spread rates in the sagebrush of 22 miles per hour clocked by a vehicle. And there wasn't a wind pushing this, this was something else altogether. Atmospheric instability, not quite sure what happened, but you just basically saw a whole hillside light up. And being able to model something that's so dynamic and these factors, it's a tremendous challenge. And I don't see how it can be done. I'm sure there are some scientists that know a lot more about the building of the models, but I don't see how it can be done.
Maybe it is a flashover, not in a contained vessel as a structure, but somehow in the wildland arena, we've got a flashover happening, whether it's terrain driven, whether there's some weather factors, whether it's, if you look at some of the common denominators, light flashy fuels, the dry dead fuels we're having, the calmness of the wind, which allows maybe the heat to build up and raise the temperature of that fuel. I don't know. I think it's just a theory and something that we should start looking at.
To take a closer look at this phenomenon, we went back to the Missoula Fire Lab to talk to Brett Butler.
I'd often wondered, what is it about fire that in many cases the people with a lot of experience say they see a whole hillside seemingly explode into or ignite all at once. From a physics standpoint, an engineering standpoint, that's difficult to imagine how that occurs. And I think that from a human factor standpoint, we could say, well, we have a difficult time keeping track of more than 2 or 3 variables. So it may be that there's multiple variables occurring at the same time, and all at once it seems like the whole thing comes on fire when it's a whole bunch of different factors coming into play. As to why a whole hillside would explode, seemingly explode all at once, I think it has to do more with the interaction between the dead fuels burning, igniting, maybe the surface fuels, and putting off enough energy that the live fuels, the live vegetation in the crowns, then participates in the fire. And then you get this seemingly broad area ignition. You know, it's always, from a scientist's standpoint, it's always important to listen to those kind of whisperings from the field, from the people that are actually on a fire. And one experience that I relate back to are the crown fire experiments we did in northwestern territories of Canada in the late 90s. And the video footage that we have of that was the cameras in the stand, and the fire burns up to and past the camera. And you see, as the fire's coming, you see, you know, it's getting brighter and brighter and closer, and then all of a sudden you kind of see this vapor, this kind of smoke coming off over a broad area, and then it almost ignites the whole area all at once, and the fire's past the camera. And it may be that what we're seeing is this type of behavior. If we assume that fuels maybe are drier, climate's a little bit drier now, so you have drier fuels over a broader area, that's impacting how the fire spreads. And that and the other thing that we saw in those in-stand videos in the crown fire experiments was the spotting, the ember shower that occurred ahead of the fire actually was a major part of the spread. So you not only are preheating the fuels, they're starting to smoke, but then you get this ember shower and you get a bunch of point ignitions everywhere. And an interesting thing from a fire physics standpoint is, if you have a point ignition, the fire will accelerate. Even the experiments we do here in our wind tunnel, we have a fuel bed that's 3 feet wide and 30 feet long. We ignite one side, one end of that fuel bed, and let it burn down the 30 or 40 feet. The first 10 feet, the fire just burns like crazy. It just goes almost instantly, and then it kind of slows down to a steady rate of spread the last 20 feet. So let's extrapolate to a real fire now in the forest. Let's assume we do have very dry conditions, and you get these embers that are coming out of the plume, spotting ahead of the fire, and so you get a point ignition. You could have that similar behavior at a kind of a small scale, where the fire burns very rapidly just at the point of that ember till it reaches a steady state, and then kind of chugs along, but then it's putting out more embers that spot ahead. And so this may be its convoluted way of saying that it may be kind of a mechanism for how fires seem to accelerate and cover a broad area in what we would, from an observational standpoint, seem to be instantaneous.
Kelly Close started his career as a wildland firefighter and later moved to the structural world in Fort Collins, Colorado. He is currently an F-band and a member of the NWCG Fire Behavior Committee. Here are his thoughts on what might be happening.
You know, I keep hearing this term, flashover, on wildland fires. And if you really look at what a flashover is, and this goes over to the structural fire world, a flashover happens when you've got fire burning in an enclosed room and you've got radiation feeding back into that room as the radiative heat bounces off walls, bounces off ceilings. It's called radiative feedback. And in that enclosed container full of combustible materials, the temperature rises and rises and rises until the temperature everywhere in the room, the air, all the fuels, everything is at the ignition temperature, and everything in that room truly does ignite all at once. That's flashover. In the wildland fire environment, we don't have the same sort of physical properties as we would in an enclosed room in a structure. It's a much more open environment. We might have some constraints by terrain, but it's generally a much more open environment. We don't have the same physical conditions that would predispose an area to what's considered to be a flashover. What we do have, what appears to be happening more and more with the drier conditions, with the volatile burning conditions is what appears to be a very rapid ignition and fire spread over a large area that's so rapid that it almost appears to be happening simultaneously across a very large area. Extreme fire behavior is a term that I hear batted around a lot. A lot of people use it. It's become a fairly common term to describe things that we didn't expect, we hadn't seen before, that are unprecedented. There's a lot of words I think you can attach to it. Really, whether extreme fire behavior is an appropriate term or not, I'm not sure. I think what we're really seeing, if you think of fire behavior as kind of a bell curve, and in the middle of that bell curve, where traditionally we've seen a certain type of fire behavior, that was a fire behavior that was behind the fire behavior prediction systems that we use, Behave Plus, the fuel models that were developed for that. That's the fire behavior that we've been seeing up until recent years. What we're starting to see now is fire behavior that's getting more and more towards that right-hand end of that bell curve. We're seeing that kind of upper end of fire behavior.
If we're dealing with fire behavior at the upper end of the bell curve, how can we begin to understand and predict it when it is outside our current modeling capabilities? Well, at this time, there are some research efforts, both here in the U.S. and other parts of the world, to improve our predictive abilities.
There's some other work by Professor Viegas in Portugal looking at how fire spreads up slopes and in the presence of chimneys. And that work is based on a relatively small set of experiments, I think like 10 or 20 experiments with a fuel bed about the size of a sheet of plywood, and they just vary the slope and the angle between the two sheets of plywood, and then watch how the fire burns up that. And that's important. It's pointing some of the directions we need to go in understanding how fire spreads, but it's not to the point yet that we probably should be using it operationally. There's important physics and understanding there, but once again, we need to keep working on this. And as well as the scientist's responsibility, keep working on it, all of us trying to understand what's happening with fire.
But in dealing with that upper end of the bell curve, we're closer from the very get-go. We're closer to that transition point. So we might go out in the morning and things may seem to be exactly what we'd expect, given the conditions. The fire behavior we're experiencing, that we're seeing, that we're observing, given the conditions, they may be exactly within what we would consider normal, but we're much closer to that threshold than we ever were before. So by afternoon, we could be crossing over into that and getting into some very extreme fire behavior, or I shouldn't use that term, getting into some very intense fire behavior, some things that we haven't seen before and that we're now calling extreme fire behavior. And I think that's the danger, is that we're starting out much closer to that transition point. And so we're not quite as clued in. We don't expect things to change that quickly and that dramatically, even just over the course of one day.
While research continues to improve our understanding of this upper-end fire behavior, there is one concept that poses significant threat to the ground firefighters, and that is the concept of a steady rate of spread versus an accelerating rate of spread.
The work that Viegas has done with accelerating fire spread in working on developing a model, I think has really helped, if nothing else, to increase our understanding of what's going on, to demonstrate to us that fires are actually accelerating, that rate of spread is not always steady state. But what it's demonstrating to us is that we've always been taught, even at the very basic fire behavior level, that given a certain set of conditions in the fire environment, you're going to have a set rate of spread and a set flame length. But now what's happening is you put fire in a different set of circumstances. You get fire that is established at the base of a very steep V-shaped canyon. It's a whole different set of conditions now, and what seems to be happening is that fire starts accelerating, moving up to some new higher rate of spread, some new higher intensity level, and probably at some point it would accelerate, and then flatten out when it reached the new steady state rate of spread or flame length. We're not seeing that because the fire usually blows out the top of the drainage before it actually has a chance to hit whatever that new steady state value is.
This rapid acceleration of fire spread obviously occurs when a fire moves from flat terrain to the base of a steep slope. But this is not the only precursor. A sudden wind increase, numerous spot fires with a high probability of ignition, or even slight variations in the fuel type can result in exponential increases in rates of spread. This was seen many times last year on flat terrain in Texas and in many parts of the Southeast. The lesson here is to understand how an accelerating rate of spread can occur and how it can compromise the effectiveness of your escape routes and safety zones.
I think it's important also for us to recognize that in terms of situational awareness, we need to be aware of what's going on, but we're very poor at keeping track of multiple variables. And we kind of assume, well, the fire is just marching along when, let's say the fire is marching along, but it reaches a point where it can involve live fuels in a few shrubs. Well, that increase in intensity could cause a rapid acceleration in the fire spread rate. Much like an example of a fire trying to cross a street, a car is coming towards you. If it's moving at a constant rate of spread, well, you look, you gauge how much time you have, you walk across. But if it's accelerating if it's a Porsche, accelerating from 40 to 80, then it's much more difficult for you to gauge how much time you have to get across that street. We need to use a similar analogy in terms of gauging the effectiveness of our escape routes. If there's a potential for fire behavior to change, forecast for a wind change, a terrain change, fires at the base of a canyon, it could move onto a slope, perhaps then we need to think about the effectiveness of that escape route in terms of a much faster spreading fire, a much higher intensity.
When people seem to be caught off guard, when things were fine a minute ago and now things have changed and suddenly they're in a very dangerous place, or they've been overcome by hot gases or a fire front, things changed quickly. We didn't expect that change to happen. We didn't expect it to happen so fast. I don't know how well we really can predict that because, again, we're getting out of the realm of what we know. We're getting out of the realm of what's normal fire behavior. We're getting into that upper end. We're crossing that threshold much sooner in the day, much sooner in the season, much more quickly. So a lot of times things will happen like a fire accelerating up a canyon, like a hot air mass moving through a canyon, through terrain features that we didn't expect. Our current fire behavior models don't predict, but I think the one thing we can do is look at just the change in conditions the last 8 or 10 years and know that, again, the live fuels are going to be contributing much more than they have in the past to fire behavior, to fire spread, and especially live fuels that have volatile compounds that, with a little bit of heat and preheating, can actually put some of those volatile gases into the surrounding air in those fuel beds. I think the one thing we can do is just expect that things are going to change a lot more quickly than we had planned, and be constantly aware. We talk about situational awareness. Be constantly aware, especially if we're working in complex terrain, that any or all these things can develop in a very short time and be honest before we expect it. So in terms of that, we need to be absolutely sure we know where our safety zone is, how long it takes to get there, and continue to reassess that during the day, because we may not have as much time as we think to get to a safety zone. We may have to be able to get there in half the time, a quarter of the time. And I think we're going to need to readjust our assessment of what's an adequate escape route, because what was adequate 10 years ago is proving to not be adequate now.
Another aspect of fire behavior that we need to talk about is the dangers of moving hot air masses in and around burning convection columns. Let's go back to Dr. Butler and listen to his observations on the Neola fire this last season in Utah, where 3 civilians died trying to protect their alfalfa field.
We wanted to go down there after that occurred and do some wind simulations, but then I looked at the pictures and you see that green alfalfa field in one spot where that came out right where they were standing. If they would have been 100 feet to the left or right, they would have been fine, probably. At one spot where you probably had this big turbulent eddy just kind of reach out and move across, just bump out into that alpha field and move back in, and it just caught them there. And we're so sensitive as humans to hot air, to injury from hot air, that it only takes a matter of seconds and you're unconscious. That's the scary thing about fire. is that we can't predict everything, and if you get too close, there's certainly a probability, a chance, possibility that you get caught in that bad location.
What the old timers tell you is good to know, listen to them, but don't bet your life on it, because we're seeing things now that they haven't seen. We're seeing a whole different game now. So learn from people that have had a lot of experience, but also be ready to change your perspective based on what you're actually seeing. Expect the unexpected. Something that I heard years ago that I really liked was this term called preoccupation with failure. Look at the situation and determine what is the worst that can happen here. And if it does happen, am I ready for it?